So you wrote down all of that. And now we're looking at IV. We're running an IV estimation. So, so this is the weighted average of the IV for always takers and never takers and compliers. Let's look at compliers effect first. This is covariance between Z and Y, right? Covariance between, let's just use the right path right away. So this is 1 multiplied by the IC, right? Because AIC was 1, right? From the DAG right there. And you are simply multiplying B according to Wright's path rules. Good. Actually, there should be expected part there. Sorry about that. Good. And probability of S being compliers. Okay. What? So their proportion here is basically, I mean, if there is only compliers, then proportion would be exactly 1, right? So always and never takers would not contribute to this estimate because there's none, right? That's the intuition of weighting. Okay. And for this part, 0 multiplied by BAN. And probability of S being A or N. Right? So AN was 0 for always and never takers was 0, right? From the DAG. They're multiplying 0 and BIAN. Right? Good. Does that make sense? Any questions so far? Nope. And then you are dividing. That's the covariance between weighted covariance between Z and Y. And now let's look at covariance between Z and T. Okay. Expected value of 1, actually, and probability of SC. And expected value of zeros multiplied by according to Wright's path rules. Any questions? Yep.
Is there a way for us to test whether there's any value in the set? Is there only
No.
just an assumption?
No. So basically, what I'm trying to suggest here, trying to demonstrate here, is that if you use IV, they would be zeros, right? So therefore, they won't matter in the IV estimate, right? And then they cancel out each other, right? And therefore, it becomes BC. So what I'm trying to suggest here is basically if you run the IB estimator estimation, then you can identify compliers' local average treatment effect. If you run the IB command in Stata, then it can give you Kate. Okay? If there is no effect heterogeneity, then you can comfortably say this is AT, right? But if there is a suspicion that there might be some effect heterogeneity, then you can say, oh, this is just for Kate. Okay. Any questions? So the intuition again here is if there's no fires, the IB estimator identifies Kate precisely because always and never takers do not contribute to the IB estimator. Right? Any questions?
So what's
So-
the meaning of local? Like
Local?
Yeah.
Local means for a specific group of people only, not the overall population.
So here
In
is
this case, Kate means just for compliers. But you cannot really pinpoint who the compliers are. That is a problem, but you can simply say for compliers. Yep.
So I think my question is there a way for us to really know whether this amplifiers in the data set?
No.
So,
The compliance classes are all latent.
so how could we decide whether it's
Oh, what?
or Kate?
Hmm?
So how could we decide if it's a local effect or is that objective effect?
How can we decide it? So you're deciding it. You're claiming you're basically estimating that BC, this effect is just for compliers, right? Except that you cannot really pinpoint whose compliers or not. That is the logic right there. What was your question? Sorry.
So how do we know is there any effect heterogeneity and is there any
Oh, how do you know if vectors have effect heterogeneity? Yeah. So it's all theoretical. It's all related to the DAG, drawing the DAG in the first place, right? So drawing the DAG in the first place, it comes from the theory, right? It's exactly that. So even adding the B, even adding the I subscription right there should be also judged by the theory. Good. Any questions? Nope. All right. In the violation of monotonicity, meaning that there is complier, then Kate will be biased. But I cannot really think of a situation where there are a lot of differentiers. Yeah, there is no good example of that. So I think it's a pretty safe assumption. Good. All right. Let's then take a 5-minute break and come back for
Give
our
us any-
argument.
So we can
Uh-huh.
We don't.
So I would say that this is
Someone told me that was
If there is compliers, it'll be compliers. That's why.
Yeah, that's I found some
你这个式子有没有搞懂？我可以跟你讲一下这样的事情。So you know why？你知道那个写这个是以前那个案子，对，在录音上。这个怎么是一，知道吗？Relation，对，然后上面是。
这边只考虑这两个其中的形象。
Yeah, you're.
very briefly though. Okay,
Yeah, that's
what is your
yeah, that's okay. So my theory is that basically
So it's now one thing we did behind. 为什么说这个可以 identify 在 causal effect？
你说这个式子，这个式子，你说的是不是这个式子？
对啊，可是它是整合
我的解释不好。
可是它是整合这两张图的情况的。
哦，
可是有没有 identify？
你看你这个，把你那个 IV 的那个 slice，
right, so I feel like
拿进去看不到。看这个，快一点，拖时间了。这个是，其实就是这个式子，
对啊，
然后再往前。
可是它都是一种情境的情况，增加的几率。
这有几种解释啊？要么就是 first stage，
对啊，
就是一个，它其实你要算一下，这个地方为什么这个减这个是等于
我觉得这有一种切换的，反正我觉得这有种切换的概念。因为以前我们在看的话，都是一张一个 tag， 然后去说，然后还有一个是这边有点结合两种情况。
查一下。
that's why I thought that. That's not. It's probably not right. It's my theory.
I'm not in good first.
I have a question.
Sure.
So you mean ID estimate identify the causal effect?
Kate only. Causal effect for average causal effect for compliers only. Compliers.
Oh, so this IV is this one.
Mm-hmm.
But what I feel like this one combines both two situations. Like,
But they don't contribute always and never takers don't contribute to the IB estimate because they are zeros.
Yeah.
They won't matter.
See, that's.
Oh, so I should just IV estimate causal effect or comply.
Yeah, compliers only. Yeah.
You know, this is.
Alright,
let's start again.
again.
So let's talk about RDD.
不知道在干嘛。
So, so RDD here, RDD is a really getting popular in sociology, and so there are some studies that are using RDDs, and they were, I think, a lot of them were published in AJS or ASR, which are top journals in sociology. So I'm definitely sensing a pattern that RDD is really getting popular in sociology and will be used a lot. Actually, the primary motivation here is, let's say the DAG or the setting you're looking at has a stark and arbitrary assignment. Okay. So, for example, let's say we're looking at students' reading scores, right? And there is a reading program for quote unquote talented kids, whatever that means. Okay. And X here is P is the treatment, and X is called an assignment variable or running variable, where this is previous reading scores. So based on the reading score of, say, the threshold of 90, those who got more than 90% in the previous reading score gets treated with the special reading, and those who didn't don't get the treatment. Does that make sense? And let's look at that. Okay. And let's look, you're looking at the outcome level, reading scores. And what you're doing here is to exploit this setting that that makes a stark and arbitrary switch in treatment, or the probability of treatment, according to the assignment rules. Okay. So you're now looking at this narrow window to estimate this jump right there. So you're saying that basically the intuition here is basically if there are some students who reported like 88% and 91%, they must be comparable, right? As long as they are similar in X levels, the levels of X, they must be comparable. The slight difference is just a random luck, right? And if you can see the jump right there, then you can attribute this jump to the treatment effect, because they're all treated and they are not treated. So more formally, it's noted as T is 1 if X is 90% and treatment is 0 if X is less than 90%. So you're trying to basically compare oranges and oranges, and try to really focus on comparing oranges and oranges and trying to estimate the causal effect of the overall population. Okay. It is a research design or identification strategy for causal effects, actually, rather than a statistical model. It's not a statistical model because it's not adjusting or controlling some variables or something like that, or coming up with a complicated model to adjust for some certain issues or something like that. You're just looking at a subset of data for higher confidence in the causal effects. It is called a natural experiment method because it's or quasi-experimental method. It's called a quasi-experimental method because it's the assignment rule is not typically made by you. The law or this random rule decided the assignment pattern, right? Even though they are comparable, they somehow got assigned to the treatment group and the control group by the arbitrariness or arbitrary threshold of the law. Good. Still, it's an experiment. Why is that? What is the core feature of experiments? For those who have taken social science methods as an undergrad, I know there are undergrads. What is the core feature of experiments? Random assignments, yes. Random assignments makes it an experiment. This research an experiment. Right? Yep. So it's a quasi-experimental method rather than a statistical model. Any questions so far? Yep.
So how we decided the threshold 90 is arbitrary or like?
This one?
Yeah.
Oh, how do you know this is arbitrary?
Yeah.
Oh, so you're theoretically deciding that, right? So 90%, is there a theoretical reason to decide someone has to be 90% to be decided to be talented? No, right? It could be 85% or 95%, 93%. There's no theoretical or inherent meaning into it, right? Just law decided it, right? For whatever reason, right? So it can be considered to be an arbitrary threshold. Good. And there are two flavors of RDD. The first one is sharp RDD. Sharp RDD means this one. All those who are over the threshold get treated. And all those who are lower than the threshold do not get treat them. But for on the other hand, fuzzy RDD allows some sort of exceptions. There could be some exceptions where even though they are over the threshold, they don't get the treatment. Some compliance issues going on. Or there could be attritions and stuff like that, but let's not complicate things too much. Yeah. So for whatever reason, there are some exceptions in that sense. Exceptions, even though they are below the threshold, they do get the treatment of reading program, and vice versa. Good. Here, in this class, we just focus on sharp RDD. Although I would like to make a note that fuzzy RDD can be estimated by the IB estimator. But what we talk about here is just sharp RDD. Any questions? Nope. There are actually two conditions of RDD. The first one is smooth trend. This should be pretty straightforward, right? Even when there is a trend looks like that, right? Can we trust this bump here as the treatment effect or not? It could be a result of random noise in the trend, right? So that's why you need to check the assumption of smooth trend by looking at the scatter plot. And the second assumption here is exchangeability. Exchangeability is about whether observations in some small neighborhood above and below the threshold are exchangeable or not, i.e. balance and covariance. Are they comparable? That is the question, right? Are they really comparable? Are they really comparable? That is the question, right? So that's the issue of exchangeability. So more on the exchangeability, Dunning suggested that it really comes down to the question of whether there is a sorting behavior or not. Sorting to the treatment or the control group, right? If sorting is possible, then let's say parents with higher aspirations will sort their children into the special reading program, whereas parents with lower parental aspirations will sort the children into the control group. Good. And there are 4 questions that should be asked about sorting, right? So to check the assumption of exchangeability, you should theoretically judge whether these 4 questions are satisfied according to the rules of RD. Good. The first question is whether agents know what the running variable is or the assignment variable is. There are same synonyms. let's look at the example right there. Do agents know whether previous reading scores, it's about whether agents or parents know previous reading scores can be a determinant in the readings program treatment. If they do, it can be a problem. Again, parents with higher aspirations, if they know previous reading scores is the mechanism of deciding the reading program, then they would try to make their kids over 90%, and vice versa. If the parents have lower aspirations, they don't really, they would sort themselves into this part. And that could affect the baseline outcome in the first place. Right? And the second question is whether agents know the threshold of the running variable. If they don't know the threshold, it may be a little bit difficult to sort the results. But then again, one can always submit a blank sheet, right, as for the previous reading score. So so that's related to my final point about this. But let me say that. Let me put it out there first. And for the third question, whether agents have incentives to sort, I would say yes. Right? If there are people who believe that the reading program actually helps in the reading achievement, and some parents might have some incentives to sort their kids to the treatment. Right? And the fourth one is whether agents have the ability to sort. They might have the ability, right? Because they can always watch the exam if you don't want to be treated. Right? So it should be really judged by the. If you don't find it really credible, my account credible, then you can theoretically judge why this is not a plausible explanation of sorted behavior, right? But my point here is that these 4 questions should be judged based on your knowledge about the setting you're looking at. So that's why you need a detailed knowledge of what's going on in your case with RDD setting, RDD method. Okay. And by looking at all of these questions, you should really integrate what is your judgment. Right? Maybe one of the questions could be violating the assumption, but then the others make it really implausible that agents sort themselves into the treatment group in the control. Right? So it should be really coming down to the question of theoretical judgment in sorting behavior. And these 4 questions should be helpful in that judgment. Yep.
Could you give one kind of example for
Whether agents do not have the ability to sort?
of course I have them.
Sure. So in the voting machine example, they did not have the ability to sort themselves, right? Because the district size was determined even before the announcement of having electric voting machine or something, right? So they did not have the ability.
One example. the agent do have the
So let's say parents make the students watch the exam, right? Even though they could have like gotten the 91% or 92%, they could have just made their kids like watch the exam. Right? Yeah.
So what is the running variable in this example? Is it
Running variable, assignment variable, running variable. Good. Any questions? Nope. The biggest limitation of RDE would be the average treatment effect within this narrow window can only be identified and estimated. So you cannot really generalize your finding to the overall population. That's the limitation.
So the late here is a little bit different from the late of IV.
Yeah,
Yeah,
it
right.
doesn't. So local average treatment effect means in general, like for IV's
Yeah.
example,
Only for compliers.
right? That was only for compliers. That's why it's called TATE, right? And it was a latent class, latent compliance class, right? But in this case, it's more observable group of people, right? Local means for a group of people, regardless of whether it's observable or not. Yep. Any questions? Oops. All right. And let's look at the STATA example. So it's the data from Angrist and Levy article published in 1999. So it's basically the education ministry in Israel implemented this rule from a 12th century rabbinic scholar who said that class size should be limited to 40 students for better education. So according to the rule, if the incoming cohort size exceeds 40, then the class will be split. Okay. And the data here, the unit of analysis here is a classroom and not individual. So I'll explain it with the explain what I mean here with some tables and some. So the reading score here is the outcome. Read variable is outcome. And size of September enrollment cohort is the running variable or assignment variable. Again, they are synonyms. Right? And intended class size is basically according to the rule of education, a Ministry of Education in Israel. So basically, size is this one. Read, and intended class size is according to the rule, how many people, how many students are there in the class. And observed class size is that it's different from the intended class size because there were some non-compliance cases and there were some attrition issues and stuff like that. But let's not care about that. Let's just focus on intended class size with the sharp RD. So as you can see right there, this is size of September enrollment cohort, right? In that cohort, how many students were there? 36, 37, 38, etc., etc. So there are 9 classes from this 36 cohort size, etc., etc. And the frequency has increased to 28 because they were split into 2 classes. As you can see from the intended class size, it was 36, right? Which is exactly the same as the size of 40, right? But after 40, the class size is now smaller because they were split into 2 groups, 2 classes. And the intended class size is 20.5. Obviously, there's still half of a person, so they had 20, a class of 20, and a class of 21. Does that make sense so far? Like, what's going on here? Yeah. And the mean reading score is all of that. As you can see, there is a jump right there in terms of reading scores. Okay. Depending on the window, you can compare these classes and say the treatment effect here is about a little less than 6 points. 6 points. Good. But you can decide the window and see how that differs by the window.
I noticed that there are other 2 gaps between the 41 and
Uh-huh.
42.
Yeah.
And 40.
So it goes down a little bit, right? So that's why you may want to increase the bandwidth a little bit, the width of the window you're looking at. It's called bandwidth, actually.
Yeah, and also the 45 and 46.
Okay. Yeah. So by looking at that, you may not see the causal effect too much, but then if you look at the general pattern right there, they're all below 70, right? But after 40 students, they're all above 70. Right? So you may see some patterns there. So to really estimate the causal effect, let's create the treatment variable. So small variable would be the treatment. If classes size is less than or equal to 40, then the treatment is 0. The splitting is 0. And then if this is greater than 40, then the class gets split. Okay. And then let's run the regression, or less regression without RD. Let's just, or to be exact, it's not without RDD, but it's more of a with the overall population. That's why. As you can see, the number of observations is 2,000 something, and coefficient is 2.59, and standard error is 0.48, which makes it significant, makes the variable significant. And let's compare it with OLS regression with the narrower bandwidth, not the overall population, within the this window, so they can be comparable with each other. So now we focused on the samples of from 38 to 43. The number of observations decreased a lot, right? It used to be 2,000 something, but it's now 100 something. And the coefficient used to be 2.59, but it's now 4.56. So we can really see that. So we can suspect that sort of we can suspect this situation, right? Without looking at the subset of the population, it's misleading, but the mean here, let's say it this way. The mean is actually a bit higher, right there, than the control group, right? But you're looking at the mean difference within the window now, so the difference gets larger. Good. And what?
But the coefficient is positive here, so by the slope
Right.
is negative.
Oh, what?
The slope,
Oh, the x-'s slope might be negative, right?
but the theta output is
So what you're looking at here, again, what you're looking at here, right, is not the slope of the assignment variable. You're not looking at that. What you're looking at here is the bump right there. It's not what you're looking at, right? The theta command gives you this bump, not the slopes of the assignment. I'm guessing like this is negative, obviously, but this is not what you're looking at. This is not what the theta actually offered. What theta offered is the difference between the mean of control group and the trigger. That's it. All right. And if you wish, you can actually add assignment variable as well. Size. It's actually it makes it positive but not significant. Okay. You can think about why this is the case, but this is basically I don't want to complicate things too much, but if you're interested in looking at why this is the case, let me know. I'll answer the question, but for now, let's just look at this one. Okay. So again, to compare the OLS with the entire quote-unquote population and the new regression, standard error has increased, right? Because, why is that? Why did the standard error increase? Yeah.
Because the number of observations dropped in this.
Yes. So we restricted the observation window to a narrow range, right? And that increases the number of observation, and that increases standard error. And let's look at the new regression model with only with the observations with the level of size levels of size of 40 and 41. And the number of observations has decreased to 37. And the coefficient is positive and higher than the previous one, but the standard error also increased as well. And as a result, the variable is not significant, statistically significant anymore at the 5% level. Good. So there is a trade-off between the identification of causal effects in terms of making the observation as comparable as possible, and the precision measure, which is standard error. Right? You have to risk that what you get as a beta estimate is a result of sampling errors. Good. Any questions? Nope. All right. And this is RDD, basically the basics of RDD. And I could see. Do you have any questions? Okay. So I could see two different ways. The first one is to elaborate more on the different strategies of interpreting logistic regression models, which will be exactly the same as the section before, but I'll clarify. I mean, it's the same, but anyways, I'll repeat the different interpretation strategies for logistic regression model, or I could just answer your questions and make it a Q&A session for the remainder of the section. What would you like? Oh wait. Huh? Oh wait. The first one? Okay. How about others? Oh wait. Don't whisper it. I cannot hear it. Oh, what? Oh, you can do both.
Well, yeah, well, both was cool. I said
Oh,
both, but.
这个 dominant variable.
Sure.
Small
Oh, I-
dominant variable. 对对对，它是 dominant variable。
What would you like?
哦，所以我才问你那个。
Okay, let's do.
我告诉你，
Is there a burning question for the midterm? Nope.
I have one. This is more of like to just kind of make sure I'm doing this right. So thinking about the difference between individual level and group level predictors, kind of this flow chart where it's like individual level predictors, individual level variance, and group level variance.
Yeah.
So
Right. Yeah. Exactly. So group level. So in the multi-level framework, the lower level predictor can explain both within variance and between variance. Why is that? Anyone?
You repeat the question.
Sure. So I'll repeat my statement. In the multi-level framework, lower level predictors or regressors, X variables, they're all sacred. They can explain both within variance and between variance. Why is that?
I'll take a step back. What is within variance and between variance? Yep. Sorry.
We have like clusters, different levels. So like we talked about schools last, or like so we have the difference like, between two different schools. So like in one level we have a difference between the people, and then even like within the school, in fact, like inside that one school or individuals.
Right. How would you know the between variance?
I feel like I already nailed.
Yeah, you did. Yeah. But then, like, how would you get that?
I was gonna do the first part.
So, between variance basically means you get the average for each school, right? And the variance of that averages, these averages will be between variance. And within variance will be after you subtract the average, school average from your score, there's gotta be some variance, right? There's gotta be some difference between your score and school's average, right? So there's gotta be a difference between your score and school's average, right? And sorry.
So like the within variance has to do with individual scores that are differing from the
School's
school's average.
Yeah.
So I know that.
Yes. How different? How variant is your score from the school? That is the between variance. Is that mine?
No. Yeah. So why a first level predictor can explain, why can a first level predictor explain both within and between variances?
Because I guess if there's like for the individual level variance, I'm thinking about test scores. So if there's like a lot of variance within the school, that can cause the schools to be like drastically different from like different in like the variance level.
Right.
But the group level predictors give an individual level, because like all the individuals have like the same like resources allocated to them by the school.
Right. I would elaborate more on the first one. So let's say we have different school averages, right? Is that solely because like school's characteristics? You're assuming that, right? But by including individual level predictors, you can explain why there is a difference in school's average. For example, let's say we have in school A, school's average is really high, and it happens to be a result of children of high economic status. It's from higher economic backgrounds, right? That's the first level predictors, right? Parental income. They happen to have a higher average because all the kids' parental income are higher than the average, right? And that's why first level predictors can explain between variance as well, not just within variance. Good. But second level predictors cannot explain within a variance because everybody has the same level of school funding. So it cannot really explain why there's a difference within the schools. Right? Everybody has the same school funding for the second level predictor, right? So that's why first level predictors can explain within variance and between variance, but second level predictors cannot explain within variance, but between variance only. Good. Any questions? Any other questions? Nope. You're all confident with the instructions? Nail it. Right. I'll explain briefly about the strategies of creating logistic regression results. So without explaining what is log odds ratio and odds ratio and all that, I'll just explain the pros and cons of that these strategies. The first strategy is log odds ratio and odds ratio, right? What is the problem with that method?
They're not intuitive.
Yeah, they're not intuitive, right? Odds ratio and odds, what do they mean? Right? Odds are not intuitive, so therefore, the first strategy, the log odds ratio and odds ratio, has a problem. All the other strategies, discrete change, marginal effect, and average marginal effect, are based on the probability scale. They're all on the probability scale. So that's why they are intuitive relatively. All right. Any questions? Nope. All right. And there are discrete change and marginal effects. What is the problem with these two methods?
Every individual has different effects.
Right. And therefore, and also related to that, it is subject to the identification of two scale issue. And this is same for the first one. Why is that? So we in the logistic regression models, right? But the thing is, we do not know the true variance of E right there. So what we do here is to create the scale factor and fix the variance of the epsilon here to 0.29. And that's the scale factor. Scale factor. Yep.
So where did you get the 3 point?
Oh, 3.29 is just that. It's a standard logistic regression distributions variance. It's the default.
Okay, so the 3.9 is the standard.
Yeah, standard logistic distributions variance. Yep.
And that's one improvement, right?
Yeah, one improvement, yes. Good. And therefore, to really estimate the logistic regression model,
the beta 1 hat, which is the estimated beta 1, here is true beta 1 divided by the scale factor that we don't know. Good. See, that's the identification of the scale issue. Right. But if you remember that the predicted p hat, the predicted probability is 1 plus 1 divided by 1 plus e minus to the minus xb, where xb is the predicted closure. Right? If the predicted logit is subject to the identification issue, then what happens to the predicted probability? It also is subject to the same issue. Good. So these three methods are all subject to the scale issue. But AME is not. Why is that? Anyone? AME is not subject to this issue. Anyone? Alright. So let's, if you remember that, let's say we have this one, latent tendency of getting, say, divorced or getting married or something like that. And then that's what we run the regression of, right? X at Y asterisk, right? Let's say we have this one, right? And then according to that, oops. God, I'm not a good artist. All right. This is the mean, predicted mean. And all of the percentage here is the proportion of experiencing this event, say 98%. And when x is, say, 1, then the predicted value is right there, right? And center is right there. And the predicted probability would be 20%. Right? Let's say we divided the scale by half. Y asterisk doesn't have a scale, right? So that's why there is the identification of the scale issue in the first place, right? Now the slope got into, became half, the half of it, the previous slope. Which means that the effect size decreased by half in terms of probability on the individual for an individual, right? But then the scale of the distribution also decreases by half.
This becomes 98%. This becomes 20% again. So even though the regression slope became in half, the overall probability, the overall predicted probability have not changed. They have not changed. So this slope means if one individual increases x value by 1, then what would happen to that individual, right? And it's subject to the identification of to scale issue, right? But on average, or for all overall population, the predicted probability predicted probabilities have not changed. That's the collapsibility issue in logistic regression model. There are other uses of terms actually, but in logistic regression model, the collapsibility issue refers to that. Good. Yep.
So just to be clear, so like the p hat value is not sensitive to like the scale factor issue.
Oh, I'm sorry.
So just to be clear, the p hat value is not sensitive to
P hat value is sensitive. This is sensitive because this logit is sensitive, right? Logistic regression model results are sensitive to scale factor issues, right? And therefore, p hat per se is sensitive. So that's why discrete changes and marginal effects interpretations are also sensitive to that issue because it's all about individual effects, right? But AME is about the average overall predicted probabilities. So that's why it's not subject to such issue. So the AME here is basically approximating the linear model's effect while trying to avoid the problems of linear probability models. Good. So again, AME is approximating linear effects while avoiding the problems of OLS, linear probability model. And that's the differences between the interpretation strategies. Any questions?
So why does those two graphs represent the AME effect? But
Oh, what?
The graphs.
What graphs? Oh, that one?
Yeah.
So
What about individual?
individual, I'm suggesting that individual effect has been become in half, right? The slope got in half, right?
Yeah.
The effect got become in half, but overall average, in terms of overall population, predicted probability has not changed. AME speaks to that one.
So it's like an area.
Right. The area is what is represented by AME.
And the slope is represented by individual.
By logit. This one, log odds ratio. And this problem directly leads to the predicted probability scale on an individual level. On the individual. Okay. So there is a difference between subject-specific interpretation. 2 and 3 are subject-specific interpretations, and 4 is population averaged interpretation. They're different. And the difference between the two really shows the collapsibility issue. I'm not saying that this is gonna come up on the midterm, but anyways.
All right. Do you have any other questions?
I feel like I've asked so many questions.
Okay.
So like
no.
for the discrete change model, the way you would interpret that is you would say the percentage change in the predicted probability.
Discrete changes also, discrete change should be interpreted as in terms of percentage point, actually. So if one person's predicted probability has increased from 10%, 0.1 to 0.2, right? Predicted probability is that. It means that predicted probability has increased by 2 times, or 10% point, or 100%. They're all same, right? So they could be interpreted in different scales, but I would definitely recommend using percentage point interpretation. Any questions? Nope. All right. Then good luck on the exam.
高中你们大概是大概几点睡几点起？ 他比我们还惨一点。像我那个时候，我高中，我觉得够惨。那时候睡都睡不好。
所以它这个 slope 会降低折会的一个 scale。
它其实是这样的。首先我们看这个，我们把这个 y 系变成一个 logic 嘛，就是 y 就等于这边是先行的，所以就是先行的，对吧？对吧？
所以说这个除一个它这边变斜率变小，原因是因为这边除了一个这个东西，是这个意思。scale
不，并不是说那个，也可以这么理解。
就是说真正的 beta one 是这个，只是你这边如果
也可以这么理解。为什么呢？它为什么要除一个东西？是要维持那个？
不要把它画乱，我先把它画背这样。
我就写的挺简单，你要维持它这个。
不是这个，
就我写一下没事。3.29，对吧？该满足这个 IB 嘛，对吧？
我们是0到3.29。
不是0到3.29，是 mean 是0，3.29是吗？不是 variance mean 是0，是这个 epsilon
对啊
的 mean 是0，
是0哦。
对，一直是0啊。基本假定就是0啊，就是说在这个这是预测点嘛。
我知道。
就上下啊，是。然后你看，好，我们现在除以 S 的时候，确实。所以这边的beta one 值是10，这是原本的。那如果我们除以 scale factor， 它会降，那这样的话就不好解释。所以他就说，这就代表individual那种感觉。然后所以他就说，他就说那个 average S 是大于
average， 它的概念是说，这个面就是一种 probability， 然后它就是
这个就是 P 了，
这个是 P。
对啊，就是这个点是 P 啊。
那这个，因为我们说这个东西看得到 average 在哪？因为这边如果都是你的 individual， 比如说旁边的 average，
这条线是 base 的。
不要写的
嫌我写的真好。
不是，等一下，我会乱写。
那个是 base one， 就是我没有加概念啊，这是 base one 呀。 那不是 baseline 不，这也是 baseline 呀。这里画的这个就是 baseline， 这个也是 x 轴没错，反正是往这个方向都是 x 轴，对吧？那这也是 baseline 啊，因为你这里也是在这个之上的，
对啊，
对吧？你这里也是在这个之上的。
那你画这个是怎么样 ？leverage 在哪里？
average 你这个图
所以这样图是
画完全，
individual 还是你这样这条线画？
你看。
我用这个用这个。
我们算那个是叫什么 MFX 吧？是 MFX 还是 MFX？ 那个简称叫
M
叫 MFX。
MFX 啊，这个从国内说
MFX 是贝塔的。
这个理解，我这理解就是所有的 observation， 就是所有的人的图片，
네, 한번 좀 쓰면 좋겠는데
你看这里是 P 嘛，
对
剩下这边是
소시올로지에서는 RD 쓸 때
어,
그냥 리니어 리그레션만 잘 돌려도
这个
망해서
你看这个斜率，我不记得这个是怎么来的，反正这个是把它所有的这
斜
个
率就是那个图里面的那个图里面的那个 B 吧，已知啊。
其实我不太理解为什么
那你可以问一下他，为什么想不到？
我不太记得啊。
他也没解释，我们是直接背、直接算、直接记、直接
我不记得这个为什么
没有这个，他直接给定义，他没有说为什么要这样，他没有说为什么要这样，他只是这样做。
快了，人家这个地方是属于上，这贝塔什么意思？
问后面他应该是 Alex，你知道吗？来问哪个？
你为什么？我从这才知道是贝塔乘以 P 乘以1.P， 或者这个，就是这个 MFX 这个。
其实它不是一个调整，就是一个所以他说的理解力是在说在这一块之间不是是在每一笔不会一样，所以它不是compare，所以他说的因素是。在某些 segregation， 它的这种在 discrete change 跟 all 跟 not all 是
Right. So individual.
那个下面是 AME， 就是 AME， 对，你还可以用。
这个先进代表是微小变化，
P 其实是关于不白的
你说的哪
P 就是这个 P 这个 P possibility 这个 P， 擦掉，哎，就是这个 P 啊，就是这个 P 啊，你看这个 P 啊 ，MFX， 这个 P 是那个 baseline 之上的那一块阴影部分嘛？是的，是的。
它这个是 marginal effect，
对，这是 marginal effect。我就说这个 marginal effect 就是，我知道这 average 为什么是 average， 但这个 marginal effect 上面是 P， 所以其实我不太明白为什么 P 是 P， 我知道 P 是什么1.P， 我也知道1.P 上面没有错，还有非常以下的那个，就是curve以下的那个，但为什么是 P？
As long as there's a
我也知道我们 base 的程度，
就是你的
So like this is all about the scale factor. Scale different, right?
对。
So if you change the scale, it is the small fraction of the plot, right? But then the slope, even though like it changes, it's still
它可能是 follow 了一个 distribution，
这个是一个投资的里面，这个是一个数理的变化嘛？对，你可以根据方式，
就是为什么是
没有讲，没有讲，没有讲。
课本上面它有讲解
Right.
你可以
Exactly. That's why population average.
钱在变化，它是这样画，对，是这样画，对，它不是。那他为什么要画这样的？然后说这个东西是那个，你这样这边画一个。
后面
这个是他在这个这区域下。
这是什么？也。所以这个是这个是个 change，
That one is the probability scale.
为什么是 P 乘1减 P？ 看这个是为什么 P 乘1减 P？ 我就不太懂。
Oh, so if you are making it to a logit model, like this is the probability scale, right? The y-axis,
没说，没说，
and then if you
Oh,
change it to logit scale, you would have that.
是真的 P 乘1减 P， 那就是1减 P 和 P 再乘以。
Oh yeah, 3D plot. Yes. Yeah, PDF. Yes. Yep.
Why is this a different IDs?